Welcome back to the second part of section 3 of chapter 10. In this one, we're going to continue looking at polar coordinates, but here we're going to see how calculus is done with polar coordinates.
Slopes of tangent lines. Now, it's kind of tempting to think, oh, we're just going to take the derivative of r and the derivative of theta. We'll have like d theta over dr, and just like we had dy over dx. But that's not the slope of a tangent line. The slope of a tangent line, regardless of our coordinate system, is still going to be the change of y over the change of x. So, when we have an equation in polar coordinates, which would look like r equals something with theta, we'll call it f of theta, we need to make this so that we can get dy over dx. Well, we know from last time that x equals r cosine theta and y equals r sine theta, which, being that r is just f of theta, we could rewrite it as x equals f of theta times cosine theta, y equals f of theta times sine theta. My goodness, doesn't that look a lot like a parametric equation? We have x equals with, we're using theta instead of t, and y equals something with theta instead of t. Oh, geez. Parametric equations and polar coordinates overlap each other. Who would have ever thought? But it's easy enough to find the derivative of a parametric equation. We just need to find dx over dt, or d theta in this case, and dy. To do this, we do need to use product rule because we have two different pieces. So to get the dx over d theta, we'll have the derivative of f of theta, which is the derivative of whatever r is. So we'll have f prime of theta times cosine theta plus f of theta times the derivative of cosine, which is negative sine, which would give us just minus f of theta sine theta. And then dy is going to be f prime of theta sine theta plus f of theta times the derivative of sine, which is just cosine. And then we can put the dy above the dx to get our derivative. It's going to be f prime of theta sine theta plus f of theta cosine theta over f prime of theta cosine theta minus f prime of, or f of theta sine theta. Doesn't that just roll off the tongue? Like, it's just so eloquent. No, it's not. It's kind of annoying, but we can find it. That's the formula. This is the formal part of it. The bottom piece down here just talks about for when it's 0. So for angles where the y value, the r value is 0, it's at the origin. So it's, and the derivative isn't 0, and cosine of it isn't 0, then the tangent line is just the slope of tangent of that. So that's just like the special case where it's going through 0 and this other doesn't work. It's tangent of whatever that angle is. So let's look at a problem here. Let's graph the cardioid. R equals 1 minus cosine theta. We're going to find the derivative of the tangent, or the slope of the tangent lines. We're going to find the derivative. If we looked at the graph of this 1 minus cosine theta, it's going to look like that. It's a cardioid that's looks like it's going to the left instead of to the right if it has a direction. So the very first thing I would do here is f of theta is just 1 minus cosine theta, and f prime of theta, the derivative of 1 minus cosine, 1 is 0, so we have cosine, which is negative sine, with that negative in front, just gives us sine theta. Now we can plug that into our equation. So dy over dx equals f prime of theta sine theta, so that's going to be sine theta times sine theta plus f of theta is 1 minus cosine theta times cosine theta over f prime of theta again, that's sine theta, times cosine theta minus f of theta, 1 minus cosine theta, times sine theta. Easy peasy. We'll simplify this just a little bit. So dy over dx equals, we have sine squared theta plus, that'll be cosine minus cosine squared over sine times cosine. Let's see, that'll be minus sine plus sine cosine. And so we can simplify some more. Dy over dx equals, so the top we almost have a Pythagorean identity. Sine squared plus cosine squared equals 1. This is sine squared minus cosine squared. Doesn't quite equal 1. However, the sine squared, we can use sine squared plus cosine squared equals 1 to get sine squared will equal 1 minus cosine squared of theta, which will leave us with only cosines in the numerator. Can be kind of nice. So we can combine our like terms there. We'll have 1 plus cosine theta minus 2 cosine squared thetas. That looks like a quadratic, so we'll be able to factor that in just a second. The denominator, we have a sine theta cosine theta, another sine theta cosine theta, so that'll be 2 sine theta cosine thetas minus sine theta. So we can factor sine theta there. So looking at factoring, we have dy over dx equals, so this numerator, I'd factor out a negative as well, because that'll get our cosine squared to be positive. So this could be negative 2 cosine squared theta plus cosine theta minus 1, allowing us to factor that. So we'll have to have a 2 cosine theta and a cosine theta. And then let's see, to be multiplied to be negative 1 is going to have to be a positive 1 and a negative 1. The positive 1 will get multiplied by 2. The negative 1 will not. So if we distribute that, we should get 2 cosine squared theta plus cosine theta minus 1. So plus 2 minus 1, yep. Then the denominator, they both have a sine in common, so we can factor out a sine theta, leaving us with 2 cosine theta minus 1. And nothing here cancels. Nothing should cancel. 2 cosine theta minus 1, 2 cosine theta minus 1. I haven't. This is plus up here. There's my problem. This is now a minus cosine, which means my signs are just backwards. Plus, and this one's a minus. Then that came from this being a plus. I saw it as a minus. That happens. Now nothing cancels. Nothing was supposed to cancel there because this is the equation for our derivative. Isn't that fun? Now, why did we simplify it so much? We simplified it because it's very possible that that's not going to be the last part of the problem. I mean, it might be. It might just be find the derivative. In which case, technically, we were done way like a few steps up. However, if things cancel, it's nice to cancel them, but it may also ask a question like, where's the slopes horizontal or vertical? It's kind of nice to know that sometimes. So let's get a clean sheet here. So when is it horizontal and vertical? So we have our equation, the graph, that's the derivative we just came up with. When would it be horizontal? When would it be vertical? It's going to be horizontal when the slope equals 0. That's when the numerator equals 0. So for horizontal, we need this numerator, 2 cosine theta plus 1 times cosine theta minus 1 to equal 0, which means either 2 cosine theta plus 1 equals 0 or cosine theta minus 1 equals 0. Here, cosine of theta would equal negative 1/2. Here, cosine of theta would equal negative 1. So what values, and this is made, these cardioids, or this cardioid, is made from 0 to 2 pi. So we don't have to keep going around and around and around. Just 0 to 2 pi. What gives us cosine of negative 1/2? Now the 1/2s are going to be the pi over 3's. We want negative 1/2. Theta will equal 2 pi over 3. Or 3 pi over 3 isn't a pi over 3, that's just 1. 4 pi over 3. And where's cosine equal negative 1? Well, that is 3 pi over 3. That's negative pi, or pi gives us negative 1. So here, the angle would be pi. So these are the places where it has a horizontal asymptote. Now, on our graph, that would happen here and here. That's the pi over 3's. And then pi is right there. It actually has a horizontal asymptote right there. If we want a vertical, we need to make the denominator equal 0. So sine of theta equals 0, or 2 cosine theta minus 1 equals 0. So if sine of theta equals 0, that's going to be 0 and 2 pi. And pi, actually. It'll equal 0 pi as well. And here, we need cosine of theta to equal positive 1/2, which, as opposed to the negative 1/2, the positive 1/2 will give us theta would equal pi over 3 and 5 pi over 3. And those would be, there. Here's the pi. Oh, cosine theta doesn't equal negative 1, equals positive 1, giving us 2 pi, which would be there, which also, notice, shows up right here. So if we're looking at it, slope's undefined. Notice here, right where we saw it was, that would be at those values, and over here. And then slopes are 0, top and bottom and middle. So that's horizontal and vertical tangents are the same as we would normally do it with a new kind of rational equation. We would find the derivative and then set the top equal to 0 for horizontal, the denominator equal to 0 for vertical. Areas. Areas bounded by polar curves. Now, we've dealt with areas a lot, and what we've always done is we've cut things into rectangles. Well, with the way polar coordinates work, that isn't going to be very easy because we don't get rectangles, we get chunks of a circle, we get sectors. And so we're going to do the same basic idea, but we're going to use a sector of a circle. Now the area of a sector of a circle is going to be the area of the full circle, pi r squared, times what part of a circle do we have? We have some theta or delta theta out of 2 pi. The pi's there cancel, so we end up with 1/2 r squared delta theta. And I know when I look at that, I'm always like, but what happened to the pi? The pi needs to be part of the area. Chances are this delta theta is going to have a pi in it. The pi comes from the angle, so that's still there. We may or may not actually have it written using a pi, but that it's still in there. So don't worry about that. Don't be afraid. It's okay. And so, but that's just for a circle. So what about if it's a curve? We're going to cut it into sectors. It's kind of like rectangles, except they're all going back to the same point. And so we're going to find each of the areas here. Now, and it's going to get better and better as that delta theta, is that angle in the middle, gets smaller and smaller where we have more sectors. We could write it as an infinite sum, but we don't need to. We would write it more as the antiderivative. It's going to be the antiderivative from a to b, or I guess in this case it would be from alpha to beta of this, the 1/2 r squared delta theta, but we want to have the same variable, so we wouldn't have r, but remember r equals some function relative to theta. So this would be alpha to beta is 1/2 times f of theta squared d theta. And remember, that's just what r equals. I mean, it's given to us. It's the equation. So that is just a basic area. But how often do we just find an area? It's never just an area. It's always going to be something kind of like that, where it's not the full area, it's only part of the area. Well, just like with like washers, we're going to take the big area minus the small area. So this is going to be the area from alpha to beta of 1/2. The big one is f of theta squared d theta minus area from alpha to beta. And alpha and beta are angles. They're theta values because it's d theta. And this is g of theta. So we have 1/2 g of theta squared d theta. And we can actually write that together because it's subtraction, so we can do the antiderivative of 1 half of f of theta minus 1 half g of theta. We can factor out the 1 half. We can actually bring the 1 half out in front of our integral. Alpha to beta of f of theta squared minus g of theta squared d theta. So this looks a lot like the Washer equations back from when we were doing volumes of rotation. And it is similar. This is just an area though. So to get the formula, this is the same thing that we just had written down, but if you like official definition-y stuff, that's for you. So let's find an area. Let's find the area of the 4-leaf rows where that's going to be 2 cosine of 2 theta. So that's going to look like that. Now something like this, a lot of times, especially since we're working with sines and cosines, if we go all the way around and do the antiderivative, we're going to get 0 minus 0. Obviously, we know that it has area. So we're going to split it up. We could split it into 2, but sometimes these go a little bit weird. This one, for instance, would start here, and as we graph it, it actually goes around like that. So going from like 0 to pi, if we just cut it in half, is going to get like the top half of these two, and then this whole bottom piece, which is kind of weird, and the top halves would equal the bottom piece, and so they would actually cancel each other out. If we went to pi over 2, we'd have the top half of this and the bottom half of that, which would cancel each other out. So I'd go all the way down to pi over 4. At pi over 4, we're just looking at this piece, that half of this. And then there's 8 halves in total, so we can just multiply this by 8. So we're going to have the area, not the volume, area equals 8 times the antiderivative. We're going to go from 0 to pi over 4 of our f of theta squared. That's this 2 cosine of 2 theta squared d theta. And then we can factor out, I forgot the 1 half that I was going to bring out to the front. So that's 4 times the antiderivative from 0 to pi over 4 of, well, we have a times 4 inside because 2 squared, then cosine squared of 2 theta d theta. So the 4 can actually get to the outside as well to give us 16 times 0 to pi over 4 of cosine squared of 2 theta, which we can use some of our trig properties. Cosine squared of theta is going to be 1 plus cosine of 2 theta over 2. Being that we already have 2 theta, this will equal 1 plus cosine of 4 theta over 2 d theta, and that will allow us to do this. If not, you could do this in the calculator to get the numeric derivative. Won't be exact, but it could still work in a pinch. So splitting this up, we have 16, 0 to pi over 4 of 1 half plus 1 half cosine of 4 theta d theta, which will give us 16 times 1/2 will be 1/2 theta. And then cosine will give us sine. So we'll have plus sine of 4 theta. The 1/2 will be there, but also there's some u substitution. There's some chain rule going on. If we take the derivative of sine of 4 theta, we'd have cosine of 4 theta times 4. So we need to divide by 4, which would turn that 1/2 into a 1/8. Then 0, pi over 4. We can plug in pi over 4 now. So we're going to get 16 times 1/2 pi over 4 will be pi over 8 plus 1/8 sine of 4 times pi over 4 is just sine of pi, and then minus, plug in 0, that'll be 0 minus 1/8 sine of 0. Let's see, sine of pi is 0, so that goes away. 0, sine of 0 is 0, so that goes away. So this is just pi over 8. 16 times pi over 8 is 2 pi. So this flower has an area of 2 pi. Isn't that neat? I know it probably didn't look like it was going to come out to be fairly nice in the middle there. So that's finding an area. We have more. Finding points of intersection. That's an important piece when finding the area. So let's use our cardioid. This is actually a slightly different cardioid. It's reflected. It's 1 plus cosine theta instead of 1 minus cosine theta. And a circle, 3 cosine theta. Graph looks like that. We're going to find the points of intersection. Well, the points of intersection are where they're equal. We have r equals and r equals. So just set the r's equal to each other. 3 cosine theta equals 1 plus cosine theta. We can subtract a cosine theta to get 2 cosine theta equals 1. So cosine theta equals 1/2, which cosine equals 1/2 when theta equals pi over 3 and 5 pi over 3, which give us this intersection and this intersection. However, as we're looking at this, what about that intersection? This equation does not give us that intersection. It looks like it intersects at the origin at 0, 0, which it does. However, if it doesn't hit it at the same theta, which is not particularly problematic, but they do intersect. If we follow the cardioid around, we get that it intersects. It has a radius of 0, which will put at the origin when theta equals pi. So it's just 0 in this direction. And then the circle hits 0 when it's at pi over 2. So it's 0 when it's going in that direction. But it doesn't matter what direction you're going in, 0 is still 0. So it does intersect there, and it's important to have that intersection point for when we do things, but there's no real way to get it from the equations. You have to look at the graph. That's really the only way to make sure that you don't miss things is to look at the graph, because there's just, like, they're there, and the equations won't necessarily tell us. So look at the graph, figure out where those are going to be, and go with that. So why would we need to find intersection points? Because, here it gives us those. So why would we need to find intersection points? Because sometimes we'll need to find areas that are bounded, and we'll have to know where they are bounded, where they intersect. So if we have that same shape, the circle and the cardioid, we have region A, region B, and region C, and we want to find the areas of each of these, we need to know where they intersect. So for region A, we'll start with region A. Region A, by the way, it looks a little bit weird. It's there, and it goes all the way down here. That line was just showing us what the line is, showing us what the outer one is minus the inner one. The outer one is the circle. The inner one is the cardioid. So to find the area of region A, we're going to have 1/2 the antiderivative. We're going to start at 0 and go to pi over 3. 0 to pi over 3 of the circle, 3 cosine theta squared, minus the cardioid, 1 plus cosine theta squared d theta. And then we're going to solve this. We're going to find the antiderivative. So a equals 1/2 times the antiderivative from 0 to pi over 3. I would start by multiplying out. This will be 9 cosine squared theta minus, that'll be 1 plus 2 cosine squared theta minus plus 1 plus 2 cosine theta plus cosine squared theta is what that one will look like. And then distribute the subtraction. So 1, it's plus 2, so it'll be minus 2 cosine theta, and then plus cosine squared, so minus cosine squared theta d theta. And then we can combine our like terms. So a is 1/2 integral from 0 to pi over 3. 9 cosine squared minus cosine squared will be 8 cosine squared theta minus 2 cosine theta minus 1 d theta. And then we can do the cosine squared again. The cosine squared was 1 plus cosine of 2 theta over 2. So this cosine squared can become 1 plus cosine 2 theta over 2. Multiply by the 8. That just makes it the numerator times 4. So we get 0 to pi over 3. We'll have 4 plus 4 cosine of 2 theta, which is something we can find the antiderivative of, minus 2 cosine theta. Again, we can find the antiderivative, minus 1. The 4 minus 1 just becomes a 3. So antiderivative, we'll have 1/2 The 3 becomes a 3 theta. The 4 cosine 2 theta, that'll be sine 2 theta, but we have to divide by 2, so that'll be plus 2 sine of 2 theta, and then minus 2 sine theta. We're going to go from 0 to pi over 3. So we can plug in, let's see, we'll have 1/2 times, plug in pi over 3. 3 times pi over 3 will just be pi, plus 2 times sine of 2 pi over 3 will be root 3 over 2, times 2 will be root 3, minus sine of pi over 2 sine pi over 3, that's going to be root 3 over 2 times root 3, so there'll be a minus root 3. And then when we plug in 0, that's going to be 0, sine of 0 is 0, sine of 0 is 0. So that's just a whole bunch of nothing. The root 3's cancel. We have 1/2 times pi, which means that the area of region A is 1/2 pi, or pi over 2. Region B, we're going to look at it pretty much the same. Region B is going to be this region right in there. So that one, we don't even need to worry about the circle. That's just going to be the cardioid. And so for the cardioid, we will have, let's see, B will equal 1/2 times the area. We're going to be going from 0 to pi over 3 again. And we're going to be taking the cardioid, which was the 1 plus cosine theta. So I'll have 1 plus cosine theta squared d theta. And so we can it just seems weird that we're doing that. Oh well. We can square 1/2 0 to pi over 3 of 1 plus 2 cosine theta plus cosine squared theta d theta. The cosine squared can once again turn into a 1 plus cosine of 2 theta over 2. So we have a 1 plus 2 cosine theta plus 1 plus cosine of 2 theta over 2, which can split up. The 1/2 can be added to the 1 to get 0 to pi over 3. That's going to be a 3/2 plus 2 cosine theta plus 1/2 cosine of 2 theta d theta. Antiderivative, we have 1/2 times 3 over 2 will be 3 theta over 2. The cosine of theta will be a sine of theta, so we have plus 2 sine theta. And then plus the cosine 2 theta will be sine 2 theta. We have to divide by 2, so it'll be plus 1/4 sine of 2 theta d theta, or no, not d theta. We're going from 0 to pi over 3. Plug in pi over 3. So we'll have pi over 3 times 3 will be pi divided by 2. So b will be 1/2. This is pi over 2 plus sine of pi over 3 was root 3 over 2 times 2, so that's a root 3 plus 1/4 times sine of 2 pi over 3 is again a root 2 or root 3 over 2, but instead of times 2 we're dividing by 4, so it'll be plus root 3 over 8. And then minus, when we plug in zeros, we get just a whole bunch of zeros. So we have pi over 2 plus root 3 plus root 3 over 8. That would be 9 root 3 over 8 plus pi over 2. Multiply through the 1/2, we'll get pi over 4 plus 9 root 3 over 16 is going to be the area of that part of the cardioid. How about the last part, region C? Region C is going to be this area up here where the cardioid is greater than this circle. So it's going to be the cardioid minus the circle. Now, it gets kind of weird because we're going to need to stop it at the axis, because otherwise we're going to get positive area, negative area. So we'll stop at the axis, we'll add both of them together. And so we will have C will be 1/2. We'll go from pi over 3 to pi over 2. Of the cardioid minus the circle. So the cardioid is 1 plus cosine theta squared minus the circle, 3 cosine theta squared d theta, plus, when we add this part in, this part, looking at it actually, we don't even need the circle. This is just the cardioid. It doesn't, the radius won't intersect the circle first. So that's just going to be the cardioid from pi over 2 to pi. So we'll have 1/2 pi over 2 to pi of the cardioid, which was 1 plus cosine theta d theta squared. So we found the first one in part A. We found the second antiderivative in part B. You guys can go through the steps of finding those without looking back. Plug in these new values, and what you will get is this area of this little region right here. That area is going to equal pi over 8. So you can again go back. You're going to see in part A and part B what those antiderivatives are. Plug in the other bounds that we're looking at to see what the area will be, or to check the area, and it is pi over 8. One last piece, arc lengths. So the arc lengths of a curve in rectangular coordinates if we have a length, it's a small length, but that's okay because we would break it into a whole bunch of small pieces. We would find this using Pythagorean theorem, where we have the change in x, but it's a really, really small change in x. So we'd have dx and dy, and that would be one little piece of L. We'd add a whole lot of pieces of L, but to find this piece of L, it's Pythagorean theorem, dx squared plus dy squared, then square root. That's L. Do this a whole bunch, add a whole bunch together, which means we are going to take the antiderivative from a to b of the square root of dx squared plus dy squared. That's the arc length for regular polar coordinates. It really doesn't change too much for, or that's not for polar, that's for regular Cartesian rectangular coordinates. Polar coordinates, it does not change. We just replace the dx and the dy with dx with respect to theta and dy with respect to theta. So for polar, what we get is the arc length is going to equal a to b, or probably alpha to beta, because we label our angles with Greek letters. We're going to have the square root dx over d theta squared plus dy over d theta squared. And what happens, if we remember that dx was f prime of theta cosine theta minus f of theta sine theta, and dy was f prime theta sine theta plus f of theta cosine theta, way back from the beginning, we found these values in the beginning of this section. So if you remember that, we can plug those in, and we can square them, and then we can do a whole bunch of calculations, and what we end up getting is, it's going to be the length alpha to beta, or the length is the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared. And what happens there is we get some Pythagorean identities, sines, cosines cancel, things like that. They all disappear. And we're just left with these pieces. So if we want to find the equation, there's, again, formal equation. If we want to find the arc length of something, like let's say the cardioid we've been working with, we have r is 1 plus cosine theta from 0 to 2 pi. We have f of theta is 1 plus cosine theta, which means f prime of theta is going to be, the 1 goes away, so we just have derivative cosine, which will be negative sine theta. So we can plug this into the equation. Now, if we did that, we would find from 0 to 2 pi, we'd get a positive area plus a negative area, and it would come out to be 0, because we'd end up plugging it in, we'd end up with 0 minus 0 equals 0, where we know that this has area. So instead of doing that, let's cut it in half where it's symmetric. It is symmetric about the x-axis. So we can look at just the top. When we cut it in half, this one goes from 0 to pi now, instead of 2 pi. So we can take the antiderivative from 0 to pi of the square root of 1 plus cosine theta squared plus negative sine theta squared, and then times 2. So we can square the pieces. 0 to pi of square root, oh, we have d theta up here. 1 plus cosine theta squared will be 1 plus 2 cosine theta plus cosine squared theta. And then negative sine squared, it'll be plus sine squared theta. Well, cosine squared plus sine squared equals 1. So that can add over. We'll have 2 times, or 2 from 0 to pi. 1 plus 1 will be 2 plus 2 cosine theta d theta. And then from there, we can go backwards from what we were doing. The going from the cosine squared to the 1 plus cosine of 2 theta over 2. Go backwards here, we have the 1/2, which can multiply out in front. We get square root of 4 times cosine squared of theta over 2. Why would we want to go back like that? Because the square root and the squared, this will get us to 2 times the antiderivative from 0 to pi. The square root of 4 cosine squared is going to be 2 cosine of theta over 2 d theta. 2 can come out, so we have 4 times, that wasn't a 4, 4 times the antiderivative, so cosine of something, the antiderivative of that is going to be sine of the something divided by the derivative of the something divided by the 1/2 gives us 2 sine of theta over 2. From 0 to pi. We can plug in pi. Sine of pi over 2 is 1, so we get 1 times 2 is 2, minus plug in 0, sine of 0 is 0, so we get 0. So we have 4 times 2, which equals 8. So what did we just find? We found the arc length. That'd be like the circumference of this cardioid is 8, which is crazy because the circumference of a circle has pi in it. The circumference of this thing, this crazy thing, is just 8. I mean, who would have thought? So, there's a bunch in this section. There is. Not gonna lie about that. There's the slopes of tangent lines, so you're finding derivatives. There are areas, which it's a big topic. There's lots of stuff going on there. And there are the arc lengths, which is, again, a topic. I mean, granted, they're just plugging things into an equation, but it's a little bit tougher than that because you have to be able to simplify and such. So this is what you'll be working on. And remember, the next few days we won't have a topic because other stuff's going on. So you do have a while and a whole weekend to be getting caught up on this. Until then, keep working problems, keep asking questions, and as always, happy mathing.